Okay, we're going to go through part 3 of this Edexcel Linear AS Level Physics Core Paper 2. Been through 2 parts already. Finished multiple choice and a couple of questions from section A in the first video. In the second one we went up to question 14, so we finished section A, and here is section B, which I mentioned to you. Section B in the linear exam can ask you slightly different questions. For example, this first one says read the extract. So this is quite a common introduction to section B, and they vary from giving you data to giving you a scenario. It's basically an application of physics questions, so they'll try and give you a slightly less familiar scenario, and they want you to be able to use your content and understanding from year 12 to be able to tackle the questions they ask you. Okay, so you shouldn't get scared by them. You just need to read it and decipher it and take out the information as you're reading it. Okay, if it's data, write down what equations you need, for example. If it's conceptual, think about which theories they're going to talk about. Okay, so let's go straight into it. If you haven't watched the first 2 parts, go back, watch them, share them, like them, and help to spread the channel with anyone who you think will benefit from watching these videos. There's also GCSE videos if you've got younger siblings or cousins who you think will benefit from looking at the IGCSE Edexcel Edexcel content that I've added recently. Okay, so it says read the extract and then answer the questions that follow. In 1933, it was predicted, it says, yeah, it was predicted that a standing wave could act as a diffraction grating. Okay, so the standing wave could act as a diffraction grating that could actually diffract electrons. Okay, so this is talking about electrons having wave properties, this wave-particle duality. The prediction was only able to be tested 70 years later when we had powerful lasers. Okay, so look at the diagram. We've got a laser here and a laser at the bottom. Okay, and then an electron beam going through the laser beam. Okay, so 2 identical lasers emitting coherent light. Now, I'm not a laser expert, but coherent, you need to know what coherent means. And coherent means that they have a constant phase difference. So in other words, they can interfere with each other. Okay? You have to ask an expert on lasers whether 2 separate lasers would actually be coherent or not. So I'm going to have to look it up myself or speak to a colleague about what we think about that. But the scenario is set that this is what they want you to assume, that they are coherent and therefore they will interact in a way that can cause interference, constructive and destructive. Okay, so they're pointed towards each other, yeah, to create a standing wave. Okay, so the standing wave is shown here as the grey area between the 2 lasers. It then says a narrow beam of electrons pass through the standing wave, and then it says the nodes, the positions of node displacement in the standing wave, act like gaps in a diffraction grating. So the distance between 2 nodes will be the d in n lambda equal d sine theta. Okay, so the d would be what they're talking about here. All right, the distance, the nodes acted like the gaps. So distance between 2 nodes would be d. Okay, I'm going to just remove this d and put a circle around it instead. So that's a crucial point to understand in the abstract that you've read. Okay. It then says the pattern of the diffracted electrons was observed by the detectors here. These are the detectors, these grey things, placed behind the standing wave as shown. So the electrons hit the standing wave, get diffracted by the nodes, and produce an interference pattern, and the central one obviously is this one, okay? And then n equals 1 is what we're interested in, because they've given us distance between, I've called it x, okay? If you can't read that writing, it's because at one stage I call it d, but then d would be confused with the d in n lambda. It's not the same. It's the fringe spacing in the interference pattern, okay? So I've put it now, called it x, okay? So this is x in my equation, okay? So once we know, I should have used tip x to just make it clearer, okay? Once we know this, and we know the distance from the laser beam, if you like, or the standing wave, and the detectors, we know this distance, and we know x, we can work out theta, because theta will be tan to the minus 1 of x over big D. And that's how you always work out the angle using the fringe spacings that you're seeing, whether you're using it with visible light or in this case with an application, with an adaptation of the idea using an electron beam, okay? The angle is always worked out by measuring the distance between the fringes on your screen and knowing the distance to the screen, okay? In this case, the screen is a set of detectors, okay? So you need to know, that's one mark to know how to get the angle. But first of all, they're going through a conceptual question. So I've explained the scenario. It says describe how a standing wave can be created, okay? Describe how a standing wave can be created. Obviously, it's from the light emitted by the two lasers. Okay. Now, remember we talked about the coherence aspect. Coherent, you've got to then say, because they're coherent, they have a constant phase relationship. Okay. You don't even need to know what it means, but you need to use those terms. So even if you find it difficult to explain to someone what does a constant phase relationship mean, and that's why I'm wondering whether two lasers will actually have a constant phase relationship. And you'd have to look into that in your own time. Don't want to make the video too long. Then if that's true, and we're going to assume it is, then the waves from the two lasers will meet and interfere or superpose, add up, or subtract, interfere. But the word is superpose. Antinodes form where two waves are in phase from the two lasers. And of course that will lead to constructive interference. So two things, knowing the difference between constructive interference and destructive interference, when they occur. Knowing that nodes occur when it's destructive and antinodes when it's constructive. These are differences that you can mention. And then the opposite of being in phase is to be in antiphase. Don't say out of phase, because antiphase means that they're exactly out of phase, so to create cancellation. Okay? And if you got all these, I've got kind of mixed up the points on the mark scheme, and you got to do what I've spoken about. That's how you get the 5 marks. So I would get the 5 marks if I wrote all that out. It's just I've kind of put it in my own way, rather than the way the examiners put it in the mark scheme. So have a look at the mark scheme and see how many marks you think you deserve. And if you're one of my students, if you disagree with anything I've marked, we can discuss that. And that's what I was talking about to one of my students today. If I think that they're close to getting another mark, I put 5+. That means find me an extra reason to give you another mark, and I'll have a look at it with you. Okay, and I think that's part of the learning experience. Okay, so then part B says a diffraction pattern is detected with a distance that I mentioned to the screen or to the detectors of 24 centimeters from the grating created by the laser light. Yeah. And the distance between the central maximum and the first order maxima, yeah, of the diffraction pattern is 55 micrometers, which I've called x. Okay, and I told you that tan theta will be x over d. Yeah, you can have a look at my diagram again if you wish. I'm not going to go back to it. Calculate the wavelength of the electrons, yeah, that pass through the standing wave created by the laser light. So we want to find the de Broglie wavelength of the standing waves, okay? And we want to do it using n lambda equals d sine theta, not the de Broglie equation, okay? Now remember, we're looking at n equals 1. We know that d is the wavelength of the standing waves divided by 2 because it's the distance between two nodes, and that will be a standing wave like that, node, node, and therefore this is half a wavelength. Therefore this distance between two nodes, which will act like the d in the diffraction grating equation, is equal to lambda over 2 because that's half a wavelength. So that's where that comes from. So that's what d is equal to because we know the laser's wavelength, okay? Okay, and there's the distance between two nodes. So then, once you know theta from tan theta, it comes to that, we can put theta into our equation as well. So we know n, we know d, and we know theta, so we know sine theta. The only unknown is lambda of the electrons. Oh, I missed it. Let's do that again. So let's put it like this in green. Final solution is all of that, all the numbers in. You'll get a mark for that. And the answer, you'll get a mark for it. 3 significant figures or 2 significant figures. The wavelength of the electrons in the beam. Okay, hope that makes sense. Here's the mark scheme for 15A, 15B. I'll let you peruse it at your whim. And 15C, we haven't done yet. There's the answers to 15C before we've done them. So 15C, what's it about? 15C says the wavelength of monochromatic light can be determined using a diffraction grating with about 500 lines per millimeter. So you could work out D, but we used the nodes in the laser beam standing wave, okay? They want you to explain why the wavelength of electrons that we were calculating cannot be determined using such a diffraction grating. Now remember, so this diffraction grating is designed for visible light, and the wavelength of the electron is much, much smaller than the diffraction grating here. And if it is, we're going to get no diffraction. So remember, for diffraction to occur, the wavelength must be roughly the same size as the gaps, okay, in the same order as. So you could work out what that is. It would be like 10 to the minus 6, and the electron beam was 10 to the minus 11. So it's nowhere near the same size. Okay. It then goes on to say, a laser produces light with discrete wavelengths. So the key word is discrete, yeah, because there are discrete energy levels that must be producing these discrete wavelengths. And it says the laser contains a gas. A current in the gas, in a laser, how they make the light, causes the atoms in the gas to move up levels in the gas atom, yeah, or molecules, and are therefore in an excited state. So telling you where the excitation comes from, it comes from the electricity, energy transfer. Explain why the excited atoms emit light with discrete wavelengths. Okay, so this is a 6-mark question. Anytime it has an asterisk, it's the quality of written communication. Okay, you get 4 marks for making points that I'm going to show you now, and then 2 marks for the quality of your reasoning, how clearly you've put your reasons down on paper. Okay, so here's my answer, or my bullet points that you could make out an answer from. Electrons can only be in certain energy states, or can only be in discrete energy levels, okay, within an atom or a molecule. Any excited atom will de-excite by its electrons falling back down to lower energy levels. So that's where dot, dot, dot implies that you could add some more detail. Each time a specific photon is emitted, yeah? Whenever there's a drop of an electron from a higher energy level to a lower one, you'll get an emission of a photon, yeah? And a photon, the frequency, yeah, or the energy of the photon is equal to the change in energy of the energy levels within the atom. So it would be like E3 minus E2, energy level 3 to energy level 2 within an atom will give you the change in energy, which gives you the photon energy, and the photon energy is HF. Okay? Only a certain number of energy transitions are possible in any atom or molecule, so only certain corresponding frequencies and therefore wavelengths of light are emitted. Because remember, we know the photon energy is HF, and HF is equivalent to HC over lambda. Okay? So they wanted you to talk about wavelengths, discrete wavelengths. So I've explained it in frequency and shown that frequency and wavelengths are inversely proportional. So if you've got specific frequencies from specific energy changes, then you're also going to get specific wavelengths only. And then you see the mark scheme to see which marks you deserve. All right, so this explains the fact that you get 4 marks for making these specific points, the content, if you like, and the rest of it will be what the examiner thinks of your ability to communicate your reasoning. Okay? So I'll let you have a look at the 6 points that they've included, which will be very similar to mine. Yeah, and it's just I use slightly different wording perhaps, but the key words like discrete need to be in your answer. certain energy states or levels, falling down, photons, emission, yeah, energy equal to the difference in energy between levels, yeah, transitions, yes, so certain permutations of transitions can be worked out if you know how many different energy levels there are. And sometimes they give you a diagram with the energy levels, and then to say that the wavelength is inversely proportional to the energy or the frequency. So as long as you show them that you know the background of the physics, you'll get your marks. The final question of this paper and the final question of this run-through. A student investigated the current potential difference relationship for a filament bulb. So we did this in GCSE with my current year 12 when I taught them in year 10. She set up a circuit as shown. 0 to 12 volts. Yeah, that means using a DC power supply, and the bulb has to be able to handle 12 volts. Okay, the student increased the output of the power supply from 0 to 12 volts in steps of 2 volts. Okay, she recorded the corresponding currents using an ammeter, and the graph she plotted is very well known to GCSE students and therefore to A-level students. You can see that the graph is non-ohmic. That means it's not a linear relationship, and is caused by the fact that the temperature doesn't stay constant. As you put more energy into the bulb, the lattice vibrations increase because of the temperature, so there's more frequent collisions, and that's what leads to resistance. So you've got to put all those ideas to get your 4 marks. Another quality of written communication, yeah, explaining the shape of the graph. Okay, a good GCSE student would be able to answer this question. So you just need to make sure you hone in your GCSE skills in preparation for this electricity question. We'll have a look at the mark scheme later. The student replaced the bulb then in the circuit with a diode and in the forward direction, a forward bias. And a resistor was added as shown. Okay, so there's the resistor and there's the diode. It's not a light emitting diode. You've got to think, how would we vary the voltage and current for a diode? Remember, the diode doesn't take that much voltage. Okay, LEDs can take slightly more, but this is not an LED. If it was, it would have arrows coming out of the diode symbol. The graph shows how current varies with PD, potential difference, in the forward bias. In other words, this is a theory graph of what it would look like. That's like what you would expect to get. It's your hypothesis. Obviously, the circuit that they've shown you isn't going to allow you to get that data. So how would you set up your circuit? And that's what the question is going to ask you. Describe how the student could adapt her method for the bulb to plot the variation of current with PD, potential difference, for the diode. Obviously in the forward bias. If you did it in a reverse bias, it would continue this way, the line, and it would give you 0 current for quite a long while. You should include any changes to the circuit. Okay, well obviously you're only going up in 0.1s, you can see that. That's the first thing to mention. So smaller voltages are needed, not 12 volts. Smaller intervals you need to consider, going up in 0.1 or less volts. Increase the voltage very gradually, yeah, especially around this point, yeah. So you can analyze exactly the threshold voltage where the current suddenly kicks in, and probably change your ammeter to a milliammeter to be more sensitive to the small changes in current, again in the same zone. And you could use a potentiometer circuit. And a potentiometer circuit is using a variable resistor in parallel with your power supply, and it allows you to take out from the variable knob on the variable resistor exactly how many volts you want. Okay, and here is the circuit that I'm referring to, that I've drawn on the mark scheme. So you see I put a variable resistor in parallel with a DC power supply, and I'm taking out of the variable resistor. Say you put it, you only need 2 volts or whatever. Say you've only got a 2 volt setting, so you do 2 volts DC power supply. Over here, maximum you'll get is 2 volts. And on this side you have 0, and your slider moves from 0 to 2 volts, and you can go in very small increments. You then want your ammeter, obviously in series with your diode, and your voltmeter in parallel with it. And that would be a circuit that would work really well. And here's the answers to 16A and 16B. So the final question is a very common question, certainly part A in GCSE, and the part B more so for AS level. You probably wouldn't use a potentiometer circuit in GCSE very often. Okay, well that brings me to the end of this run through. I hope you found it useful and it helps you with your preparation towards the end of your year 12 course. And here's all the equations you get while I'm finishing off the video. So once again, there are 3 videos in this playlist: part 1, part 2, and part 3. This is the end of part 3. Thanks for watching. Like, share, and subscribe. Please help the channel reach more students. And if you're one of my students, make sure you improve your communication skills. Bye for now.